We're going to start this session today. Just a reminder, please feel free to ask questions. You can unmute yourself to ask the question. I encourage you to do so. If you're doubting your own internet connection, or perhaps you would rather post it in the chat, you can also do that, and I will read the question. And I also wanted to remind everyone that after the two talks, we're going to have some time for a more informal discussion off the record. So if you have very controversial questions that you don't want to be recorded, please feel free also to wait till the end of the two talks and ask your questions there. And with that being said, we're very happy to start with Geoff that will tell us about the Python's lunch. Please, Geoff, take it away.
Let me share my screen.
Yeah.
Okay, awesome. So yeah, this talk is going to be about this paper that I put out last December with Adam Brown, Grant Grobizian, and Lenny Suskind, called Python's Lunch, Geometric Obstructions to Decoding Hawking Radiation. And it's really based in large part on some seminal earlier work by de Saint-Exupéry. Okay, so what's this talk going to be about? Well, in the first part, I'm just going to be reviewing stuff from a load of papers written by me and many other people over the last year or so about how we can use semi-classical gravity calculations to see that information that falls into a black hole comes back out in the Hawking radiation. But then in the main part of this talk, which is actually about this paper, about Python's lunch, yeah, so that will be largely based on my paper from May. In the main part of the talk is going to be about how we can see from the semi-classical gravity description that the information that falls in the black hole can't ever be reconstructed from the Hawking radiation. So I'm not actually trying to overturn the first part of my talk with the second part of my talk. That would be slightly perverse. So there is another difference between these two parts, which is that the first part is about what is possible to do in principle. And in the second part, we're talking about what's actually possible to learn in practice. So to be a bit more specific, in the first part, I'll be showing that sort of after the page time, the Hawking radiation encodes information about the stuff that falls in a sort of Shannon theory information theoretic sense. Whereas in the second part, the main part of the talk, I'm going to be trying to argue that actually reconstructing that information and getting it into a simple form that we can use is exponentially complicated. And it's exponential in the entropy of the black hole, which for a solar mass black hole is like 10 to the 77 or something. So this is order e to the 10 to the 77, which is a very, very big number. So in practice, it is just completely impossible. And there's another difference between what we're going to be doing in these two parts. In the first part, I'm not going to be doing anything, but every claim I'm going to be making is going to be based on very precise gravitational calculations. You can do like replica trick calculations. You make precise arguments over exactly why it's all true. And in the second part of the talk, it's going to be very different. We're going to have a few like technical calculations that don't involve gravity directly, and then we're going to have some words about how gravity maybe is analogous to those calculations. So obviously it's a much less strong result in that sense. And my excuse for that is really the following. It's that there is a very big difference between complexity theory and information theory, which is that, Claude Shannon was a very smart guy, but he sort of single-handedly proved most of the fundamental theorems you would want to have about information theory, noisy channel coding, noisy source coding, everything like that, he just did himself. Whereas the sort of central things you might want to know about complexity theory, we generally don't have a clue on. So complexity theory is just, I think, fundamentally harder than information theory. So that's really our excuse for having much less to say or much less precise things to say. But I guess the point of this conference is to try and tackle those hard questions anyway. Okay, so let's start with just reviewing this argument that in principle you can see that the information has to be coming out. And I'm not going to give the sort of technical arguments involving replica tricks. I'm just going to try and give some intuition, sort of all the intuition of how the result works that will be necessary for the second half of the talk. And really that intuition is going to involve the sort of connection or the analogy between ADS CFT and tensor networks. So how is this analogy meant to work? Well, the idea is that sort of ADS CFT is roughly analogous to a sort of tensor network, which is the bulk description of some state that the tensor network prepares, and that's the boundary description. So if that's the case, then if you look at the sort of entanglement entropy of one part of the boundary, then it's easy to see from the tensor network description that it is upper bounded by the sort of number of legs of the tensor network, the minimum number of legs of the tensor network that you need to cut to separate the two parts of the boundary, multiplied by the log of the dimension of each sort of tensor network bond. And for random tensor networks, at least, and certain other classes, then this bound is in fact close to saturated. So it's not just an inequality, it's actually an equality. In ADS CFT, the sort of number of tensor network legs is going to be proportional to the area. It's going to correspond to area over 4G Newton. This is going to connect to something called the reattacking formula. I'll talk a bit more in a couple of slides. We can also sort of add bulk fields into this tensor network time model to make a slightly more realistic description of ADS CFT. And the way we do that is that we just add sort of dangling bulk legs. These red dots are sort of legs sticking up out of the page. And this makes the overall tensor network now sort of a map from the bulk state of the bulk fields and all these red dots out to the boundary state. This map is generally an isometry, at least when you have no black holes. So now, depending on the bulk state we consider, then for some boundary state, the sort of bulk fields may be entangled across the RT surface. I've drawn that schematically with some bell pairs entangled across the two sides, but in general, it can be a lot more complicated. And this entanglement of the bulk fields across the surface sort of adds to the boundary entanglement entropy. So now, rather than just having the area, rather than just having the number of cuts, then it's the number of cuts through the network plus the entanglement entropy of the bulk fields. It's something called the generalized entropy, A over 4G Newton plus the sort of bulk entanglement. And now an important point is the sort of minimal cut is no longer necessarily the sort of cut that minimizes the number of tensor network bonds we're cutting, no longer necessarily the minimal area surface. It's now the sort of cut of minimal generalized entropy. That's the one that's going to give you the sort of best bound, best upper bound, and that's the upper bound that's going to be actually saturated. Okay, so the final thing we're going to see in these tensor networks is something called entanglement wedge reconstruction. So what is that? Well, it's about the question of, let's say we only know the reduced state of the boundary on some subregion. And we want to know how much we can learn about the bulk state by knowing that reduced boundary state. What's the answer? Well, it's just everything between that boundary region and this RT surface. It's called the entanglement wedge. Why is that? Well, it's because if you look at the map from all these little red legs within that region, plus all the legs on the RT surface to the boundary, then it's approximately an isometry. Okay? And so that means we can sort of, you know, the information in this region gets locally preserved on this boundary. Okay, so that was all in tensor networks. What about actual ADS CFT? Well, suppose we consider some semi-classical bulk state in ADS CFT, and for the moment we're going to take it to be static. Then we can again look at the reduced state of the boundary on some region. And there are two facts that are sort of well established at this point in ADS CFT, which is one, The entanglement entropy of that boundary region is given by the generalized entropy of the sort of minimal generalized entropy cut. This is something called the quantum extremal surface prescription for the entanglement entropy. And if I have some bulk fields or some objects, say a diary, sitting between the boundary region and the surface, quantum extremal surface, then it can be decoded from the boundary region. So just like in tensor networks, we have this sort of Ryutaki-Nagy formula, quantum generalization of it, and we have a notion of entanglement. So the analogy between tensor networks and ADS-CFT at least seems to hold with these two pretty central facts. And in fact, there's at this point, we also know it goes beyond that. There's things like non-perturbative corrections that you can calculate in the two different things, random tensor networks and ADS-CFT, and again, you see the sort of same effects. So it seems to go at least reasonably. And yeah, later in the talk, we're going to be really relying on that analogy being true in some even deeper sense. So hopefully it is. Okay,
sorry, question. Can you comment a bit more about what type of non-perturbative corrections you're talking about?
Yeah, sure. So let's say rather than just having sort of a simple boundary region, we have like say two separate boundary regions. So now we have sort of two extremal surfaces rather than one. There's sort of a surface that goes like this and like this maybe, and then there's one that goes like this and like this. And then you can look at the corrections you get when the sort of generalized entropy of those two surfaces is pretty similar. And at least in a slightly simplified setting where the areas of those surfaces are fixed, then it turns out you find exactly the same sort of non-perturbative corrections in random tensor networks as you do in gravity. So this is discussed in my paper in November with Stanford, Schenker, and Yang on replica wormholes in the black hole interior. I think for the general case, we talk about it in some appendix, which should be visible in the VT.
Thanks.
Yeah. Okay, so what does this have to do with black holes? Well, let's talk about black holes in anti-de Sitter space. The first thing to note is that if you have a black hole in anti-de Sitter space, then it doesn't naturally evaporate. So what happens is you get some Hawking radiation that's entangled with the interior of the black hole, but then that Hawking radiation gets out to the sort of time-like boundary, and it just reflects back in. And so you quickly reach a sort of thermal equilibrium. Unless the black hole is so tiny that the black hole is already evaporated by the time that can happen, but we're not going to be worrying about that. But this is something we can change pretty easily just by changing the boundary conditions at the boundary of ADS. So we just change them so that rather than this Hawking radiation getting reflected, it just gets absorbed. And we're going to make it be absorbed sort of into another system. It can take to be a sort of second holographic CFT. So now we actually have an evaporating black hole, and intuitions about unitary black hole evaporation suggest that the sort of entanglement entropy between the two CFTs should follow the page curve. It should go up until the black hole is roughly halfway evaporated, and then it should start going back down. Okay. So now we're going to bring our tensor network analogy in. And I emphasize that there's sort of stronger arguments for all the results I'm going to say in this section, but we can see the intuition from tensor networks. So we're going to assume that there's some bulk slice through this sort of geometry of two bulk systems that is analogous to a tensor network, okay? In exactly the same way we had an analogy before. And one very important and natural question is that this is not a static space-time geometry, and so there's not sort of a preferred slice through the bulk. So there's a question of, okay, if you say a bulk slice is analogous to a tensor network, then which slice are you talking about? And it's pretty easy to see that it can't be sort of every slice. That gives nonsense. But what I'm going to sort of assume for the moment, and this is sort of justified assumption, at least qualitatively, is that we can consider what's called a nice slice. And that, roughly speaking, can take to be a slice that sort of goes inside the black hole, and then it sort of sits at some radius that's a sort of fixed small amount inside the event horizon, goes all the way along all the way deep into the black hole, and then eventually it just goes to the origin as the collapsing star or whatever is somewhere deep down here, and then it just does whatever once it reaches that point. Okay. So yeah, it turns out that at least qualitatively this will give us the right answers. So what does this slice look like? Well, it looks very schematically like this. Okay, so you should think of this as sort of, you know, this weird wiggly geometry I've drawn is meant to be the sort of wormhole, sometimes called one-sided wormhole, sometimes called sort of a bridge to nowhere. So out here we have sort of the flat ADS space. Imagine this being rotated into a sort of cylindrical-like thing. So we just have a sort of round, flat mouth of the wormhole up here, like one of those you know, stupid models of general relativity as a sort of trampoline getting warped by some huge mass, except I've turned it sideways. So this is the part of the trampoline that hasn't got warped yet. And then we sort of have the horizon, and then we have this sort of deep, saggy, deep sort of hole that's the black hole that's getting longer and longer over time. For the slice we've chosen, then there's sort of interior partners of the Hawking radiation that are sort of equally distributed along the length of this wormhole. So I've drawn them schematically here as being bell pairs entangled with this second copy of the bulk, which is this disk over here. Okay. And the sort of width of this thing is meant to represent the sort of area of the wormhole at that point. So in particular, up near the horizon, it's sort of the narrowest point, and as we go deeper into the wormhole, we effectively go back and back and back in time, and it gets bigger and bigger because the black hole is evaporating. Okay, and as I said, all these lines just represent the sort of bulk entanglement between the interior modes and the wormhole, and the modes that escaped into this second holographic CFT. Okay. So now we're going to think of this as a tensor network, where again we have a sort of network where the number of legs is proportional to the area, but we also have legs, the bulk legs from the bulk entanglement. And we can look at the sort of minimal cuts, or the potential minimal cuts between the sort of two holographic CFTs, the one over here and the one at the end over here. And there's two cuts that can potentially be the smallest. One is the sort of narrowest point in this wormhole, right, where you aren't really cutting through any bulk entanglement, or not very much anyway, and the area is sort of at its smallest point. But then there's another one, and that's the one where you just sort of don't cut through any actual area at all. You just cut through the bulk entanglement between the interior modes and the Hawking radiation. And what turns out to be the case, so yeah, so the size of these two cuts, the size of this one is basically the area of the horizon over 4G Newton, and the size of this one is sort of the sort of semi-classical entanglement entry, the answer Hawking would have given for the entanglement entry between the Hawking radiation and the interior. So before the page time, by definition, it's this first cut that's smaller, the cut that cuts through the bulk entanglement between interior and Hawking. So what does this mean? Well, firstly, it means that the entanglement entry of the black hole is given by the naive Hawking answer. We get the first half of the page curve. But it also means that we have some sort of diary sitting deep in this black hole, then that's on the black hole side of the cut. By analogy with the tensor network, we can sort of push it through the tensor network and get it out to the original CFT. It means no information about the diary has escaped into the Hawking radiation because it's all still sitting in the sort of original CFT. Okay, what about after the page time? Well, now, instead, the sort of minimal cut is the one that cuts through near the horizon. Okay, so now the entanglement entry is instead given by the area of the horizon. We have the second half of the page curve where the entanglement entropy starts going down. And we also have that if I have some diary slipping deep in this black hole, then it's now on the Hawking radiation side of this minimal cut. And by analogy with a tensor network, we can sort of push it out to the Hawking radiation. I.e., if we have access to that second holographic CFT, or equivalently, if we just have access to the Hawking radiation, then we, in principle, should be able to decode the information of the diary. The information in the diary somehow affects the microscopic state of that second holographic CFT. Okay, so that was just a very high-level overview, because hopefully many people are sort of vaguely familiar with that story by now. But I want to make a few more comments before we go on to talking about complexity. So the first one is that, I just sort of chose an arbitrary slice there, but really the sort of correct slice where this tensor network analogy is actually valid is one that maximizes the size of that minimal cut. Okay, this is something called the max-min prescription for the quantum extremal surface, established for the sort of classical case by Aaron Wall back in 2013, I think. And paper in December by me, Netta Engelhardt, Chris Akers, and Misha Usachuk, where we showed that it also in the quantum case, it's sort of equivalent to the more standard quantum extremal surface prescription. Okay, so what, in conclusion, that not every slice is actually analogous to a tensor network, but there's some set that are, and they're the ones that maximize the size of the minimal cut, so contain the sort of quantum extremal surface. So if you sort of actually do a covariant analysis, you don't just consider one slice, you consider either all slices and maximize over them, or you just look for the quantum extremal surfaces. Then the sort of qualitative analysis we just did is exactly the same. The entropy goes up, then it goes down. Information in the interior starts being accessible after the page time. But also, and sort of more excitingly, you find exactly the right delay for being able to decode information that was thrown in after the page time. And that's something called the scrambling time. And yeah, to get that, it really is crucial that you actually do this full covariant analysis. Like a sort of naive tensor network toy model wouldn't know about this, but gravity does. It's really quite amazing. I also want to emphasize that, I said a lot of words about analogies with tensor networks, but there was absolutely no need to say anything about that to derive everything I just did. Really, all it comes from is just doing the gravitational path integral and doing something called the replica trick to calculate entropies. And you can use something called the PETS map to calculate whether the information has got out or not. But the important thing is that when you do those things, you include topologies that contain so-called space-time wormholes. And these wormholes can connect different replicas together, and everything can be derived pretty rigorously. On the other hand, for everything that's going to follow from this point on, that is not true at all. We're really going to be relying on this analogy with tensor networks and sort of guessing that it will continue to hold for questions about complexity. Okay, so let's move on without further ado to the question of why is it so hard to extract information from the Hawking radiation in practice? So I guess the first question is it hard? Well, this was very famously argued by my advisor, Patrick Hayden and Dan Harlow, back in 2013. In particular, they argued that if you have sort of black hole plus Hawking radiation, then the complexity of sort of decoding that state into something very simple, where we could say recover information that fell in, or sort of test for a violation of the Amps paradox or anything like that, is exponentially hard in the entropy of the black hole, as I claimed earlier. On the other hand, sort of starting in 2014 and over the years since, there's been these ideas by Susskind and collaborators that this complexity of a state in ADS-CFT, on the CFT side in ADS-CFT, is actually due to sort of the volume in the bulk of a maximal volume slice, or roughly equivalently the action of the so-called Wheeler-DeWitt patch. And for an evaporating black hole, even after the page time, this is something that's easy to calculate, and it's of order the entropy of the black hole. So at least very naively, there is a big difference between these two quantities, an exponentially large difference. So is this a contradiction? Well, okay, so the complexity equals action stuff is pretty speculative. So there's one possibility would be that's all just wrong. Lenny just has lost it in his old age. But it certainly is true that you literally can make the state in a order entropy time. All you do is you just create the black hole and then allow it to evaporate until you reach the state you want, right? That just uses the Hamiltonian for an order entropy time. It's certainly not an exponentially complex thing to do. So at least in this circumstance, then Lenny and everyone else is right. So maybe Patrick and Dan Harlow just screwed up somewhere. Well, no, I mean, they obviously knew the thing I just said, right? That you can make the state in a small time. So the answer actually is that these two things are just talking about different definitions of the complexity of the state. In particular, they just have different rules for what you're allowed to do to make the state or convert it back into a simple state.
Sorry, Geoff, question?
Yep.
So, the complexity equals action, say you could derive it. That's supposed to be the leading contribution. The volume or action would be the leading contribution, but then there would be a quantum correction to that. Much like in entanglement entropy, we have an S bulk. Yep. So could we not imagine also that, same thing happens for complexity? There's some sort of piece that's typically small and suppressed by 1/n, but for the same reason that in the page time you need to take it into account, something similar would happen for complexity?
Yep, no, that's a very good question. I have two answers. First, we know that the complexity of making the state in this case is actually very simple, right? The second is, at least in analogy with tensor networks, you would have thought the sort of quantum correction would be like the complexity of the bulk state, right? Or even in analogy with the entropy thing, right? The quantum correction for entanglement entropy is the bulk entanglement entropy. I think it's reasonably easy to conclude that the right sort of quantum correction to the holographic complexity is the complexity of the bulk state. And in evaporating black hole, that's always very simple. It's just a basic, roughly speaking, a loaded product. But yeah, really the answer is just that the definition of complexity that's being used in complexity equals action, then an evaporating black hole, it just is small, right? Because you can just make the state by evaporating black hole, and that's not very hard to do. To unmake it, you just time reverse and let it all go back into the black hole, and the black hole disappears. So yeah, so what's the difference with what Harlow and Hayden were saying? So let's say you started with some simple entangled state of a bipartite system, okay? Then you can imagine applying sort of separate unitary circuits to each side and try to do that to produce the desired state, okay? And if the desired state is maximally entangled, actually you only need to act on one side. You can sort of move all the stuff circuit applied on this side over and just apply it sort of here instead. But yeah, that is one set of rules for what you can mean by the sort of complexity of making or unmaking a entangled bipartite state. Ooh, that didn't mean to happen. Okay. So this is the sort of right definition if you want to know how simple it is to start with some, to start with the state of the evaporating black hole and then act sort of only on the Hawking radiation, for example, and then make some simple state out of it, say the thermofield double. Right? In this case, we're only allowed to act on the Hawking radiation. We're not able to act on the black hole at all. We just don't have access to that for the decoding we're trying to do. And so we're only allowed to consider these circuits where the two sides don't interact. And there's a natural sort of other definition which just says, forget about the fact that it's bipartite. Just apply any unitaries you want as long as they're sort of k-local or whatever. But they're allowed to couple the two sides together however you like. So this is what we've drawn here with these red lines schematically indicating coupling the two sides. But more generally, the coupling can be a lot more complicated than that. And so this is the definition whether the complexity of the evaporating black hole is not very large, right? Because we can just start with the simple state and then just evolve it of the black hole first forming, and then just evolve it forwards in time, gradually take out Hawking radiation. So effectively what we're doing is we're completely coupling everything together in a complicated way, but eventually we end up with this bipartite state on the two sides again, and that's the state of the evaporating black hole. Yeah, so when everything's in the black hole, then everything was just totally coupled together in some crazy way. We think the black holes roughly look like sort of all-to-all couplings. And so, yeah, that's the rules where we find this small complexity. But that just sort of changes the question we have to ask from why does there seem to be a contradiction between Harlow-Hayden and complexity equals action to a new question, which is why in an evaporating black hole is the restricted complexity much, much, much bigger than the unrestricted complexity. So to make it clear that this isn't something that sort of inevitably happens, let's just imagine taking the thermofield double state and then time evolving one side for an order entropy time, right? In this case, everything's the same. We created the state by starting with something simple and just evolving one side. The restricted complexity is order the entropy, but the volume of it, or the action is the length of the wormhole, which is also order the entropy. And so that presumably is also the unrestricted complexity, and it's reasonably clear there's no like shortcut, because everything is the same and comparatively small. But in both cases, we have an order entropy length wormhole. So it's very natural to ask the question of what's the difference between this and evaporating black hole? In particular, or more specifically, how just by looking at the two semi-classical geometries, can we see that in one case, the restricted complexity is exponentially large, while the unrestricted complexity is still small, and the other, they're sort of both small. What's the difference between the two? And our answer, our sort of conjecture, is that the difference is that evaporating black holes contain a Python's lunch. Okay, so I'm finally ready to introduce the idea of Python's lunch. So what is it? Well, in a tensor network context, we just mean something like this. So you can think of this as a bipartite tensor network, roughly like a wormhole. We have two ends, sort of bipartite entangled state, and we have a lot of tensors. I assume all these tensors are sort of either unitaries, where it's sort of two things coming together and then two going apart, or they're isometries, right? So here we have sort of one leg coming in and then two coming out. And here again, we have one coming in and two going out. So these I'm going to assume are unitaries, except we have some ancillar qubits here that are just fixed to be in the zero state. Okay? So if we assume this is a random tensor network, then generically we'll find that so long as the sort of left-hand end is smaller than the right-hand end, then the entire network will be very, very close to an isometry when looked at as a map from left to right. Equivalently, as a state, it will be very close to being maximally entangled on the left-hand end. However, even though this is a sort of comparatively simple tensor network, let's say it sort of has order SBH in length, then that doesn't necessarily mean that the isometry it describes is a simple isometry. And the reason for that is that even though the whole thing is an isometry, the individual steps in the network are not. Let me make that a bit more precise. So yeah, in particular, as we sort of go from left to right, as we go from sort of here to here, the size of the network gets smaller, so that individual step is not an isometry. It's only when you compose it with the isometry from the start of the network to here that it becomes an isometry. So just to be very explicit about this, in equations, we can think of this tensor network as a map from some input state I to some output state, input state on the left I, to some output state on the right psi. Okay? And what does this network do? Well, the first thing that happens is we have some bit where it sort of gets bigger in size. So that means we get a load of extra ancilla qubits added in, all fixed in the 0 state, right? So the system gets bigger. We also have a load of unitary evolution. I'm going to call U tensor network. So this is all the actual individual unitaries in the tensor network, including the ones in the isometries, where we're just going to treat them as unitaries with some extra ancilla qubits added or taken away. And so this is comparatively simple if the tensor network is simple. And then finally, we have this bit where the sort of tensor network gets smaller. And that means we have some ancilla qubits in a 0 state, but now rather than being kets, they're now bras. So now we're post-selecting onto those qubits, all being in the 0 state. And in particular, as a sort of individual step, this is not unitary. Okay, it's very non-unitary. It's selecting on a particular measurement outcome. However, because the whole thing is unitary, then it should be the case that we can find some unitary map that I'm going to call UPL, U Python's lunch, that just takes this state I plus the ancilla qubits and outputs the state psi plus the ancilla qubits. In other words, we can do the whole thing without post-selection, but it's not necessarily obvious how to do it just from looking at the structure of the tensor. And the question is whether this UPL is simple to do, if U tensor network is simple to do. And our answer is very definitely no. So how hard is it to sort of bypass that post-selection and convert that into a purely unitary process? Well, let's just think about the sort of stupidest thing you could possibly do. Let's say rather than having just one copy of the input state I, let's say you could just prepare it as many times as you want. Let's also say you were allowed to do measurements. Okay, this isn't quite the rules we have, but it will give roughly the right answer and it's useful intuition. Then what you can do is you can just prepare the state, apply U tensor network, and then measure the ancilla qubits you want to post-select on, and probably you don't get an answer of all zeros, so then you go, oh well, try again, and you just keep doing it, keep trying until you get really, really lucky and you get all zeros, and then you go, great, I did it, I made the state I want. How long do you have to do this? Well, if I have MR qubits I'm wanting to post-select on, then the probability of getting the right answer is roughly 2 to the minus MR. So the time is sort of order 2 to the MR. So it's exponentially hard. Also, we needed to be allowed to do measurements and be allowed to prepare the initial state lots and lots of times, so it isn't even unitary. Now, this is quite bad. But we can do a bit better on every front. And that's by using something called Grover search. So how does this work? Okay. So what you do basically is you start with your input state and all your ancilla qubits in 0. Then you apply this U tensor network, a simple unitary that describes the tensor network evolution, ignoring the post-selection. Then, if and only if every ancilla qubit is in the 0 state, you apply a phase of -1. Okay, this is a sort of pretty simple thing to do. Now you apply U tensor network. So that changes the state very, very slightly, because there was only a tiny probability of being in that state in the first place. Now we apply U tensor network dagger. So we evolve sort of backwards in time. And now we apply a phase of -1, if and only if all the ML initial ancilla qubits are in the 0 state. Now we just go backwards and forth, keep doing this, 2 to the MR over 2 times, and magically the sort of state at the end very slowly rotates from the non-post-selected state into the post-selected state. Very clever and magical. Grover search is super cool, but it works. But the key point is that 2 to the MR over 2, we got a square root improvement, but it's still exponentially hard. Okay, so that's a bit better, but maybe there's something like still quicker that will just do it, no time at all, order the entropy time or whatever, or polynomial in the entropy. And maybe that's true. Complexity theory is hard. No one knows anything. It is known that sort of if you're doing a black box sort of search strategy, then Grover search is optimal. So that's kind of hopeful. But in this case, Sorry for the typo. We sort of know in advance what we're searching for, right? There's some structure to the problem. So there definitely could, in principle, be more efficient approaches. There's reasonably good reasons to think that even if you sort of know what you're post-selecting on, then in general, it can't be done in polynomial time. And that's because this would basically imply that BQP is equal to PP. So what does that mean? So yeah, BQP would be equal to BQP with post-selection, which would be equal to PP. So BQP is like what you can do with a quantum computer in polynomial time. Post-BQP is what you can do with a quantum computer if you're allowed to sort of cheat on post-selection. And PP is a particular classical complexity class that is very, very powerful. So if you're not a complexity theorist, you might think like maybe this is true, maybe it isn't. But if you suggest it's true to Scott Aronson, then he'll like laugh at you. So yeah, basically I think we should trust him. He knows a lot more about this than any of the rest of us. So almost certainly isn't true that you can sort of generically simulate post-selection in polynomials. So one can sort of vaguely, reasonably, if somewhat speculatively, make the following conjecture, which is basically that generically for a tensor network, Grover search is as good as you can do. So the restricted complexity of the sort of state you produce is sort of the complexity of the original tensor network, complexity of sort of UTN, times 2 to the number of qubits you post-select on divided by 2. Okay, so what does this have to do with gravity? Well, sort of the ordinary sort of wormhole that you get if you say time evolved the thermofield double state roughly looks like this. You start at the left boundary, get smaller, 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 reaches the smallest point in the middle, then it gets bigger, bigger, bigger again, reaches a larger point. I claim that this corresponds to sort of a tensor network that just gets smaller and then gets bigger, and it has small restricted complexity. I'm going to call a Python's lunch wormhole something that instead looks like this. It gets smaller, 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 then it gets bigger, bigger, bigger. It has a bulge in the middle. The Python has eaten a very large lunch and got a bulge. Then it gets a bit smaller again. Maybe it doesn't get quite as small as it originally was, and then it gets bigger. And we conjecture that this is like the tensor network that gets small, big, small, and that this has an exponentially large restricted complexity. Okay, so what does this have to do with an evaporating black hole? Well, go back to our story earlier about this nice slice. Again, we have these sort of two restrictions with a bulge in the middle. Just one of them is sort of much more like quantum restriction, right? So you'd say here, the sort of size of the cut is all cutting through the quantum bulk entanglement, or if we believe in ER equals EPR, maybe there's sort of micro, like Planckian wormholes. And this one here is just cutting through the main throat of the wormhole. But it's nonetheless true that if I sort of start here and I sort of try to sweep my way over, taking cuts that sort of smoothly go from this cut over here all the way to a cut that maybe goes through here and then one that goes through here, then I have a bulge, right? The generalized entropy will go up and then it will go back down. Claim that this is Python's lunch and that this explains the really high complexity of doing Harlow-Hayden. Okay, so now we want to know how big the Python's lunch is. Well, the first thing, because then we can sort of actually make a precise conjecture for how hard Harlow-Hayden is to do. So the first thing to note is that the sort of maximum size of the lunch depends on how you slice through from one constriction to the other. Okay? Same thing is true in tensor networks. We can cut through the tensor networks. We can apply the tensors in the tensor network unitaries in various different orders. And depending on the order we do, then we'll have a different amount of post-selection. Right? And in general, the sort of slicing that minimizes the maximum size of the bulge is going to require the least post-selection. It's going to be the most efficient Grover search protocol. That's the thing that's going to determine the complexity. So what's the sort of most efficient way to slice through this evaporating black hole, Python's lunch? Well, one way is the following. You just start cutting through the bulk entanglement, and then you sort of add in an extra cut at the end of the wormhole, and then you gradually move that cut along until you eventually end up just cutting through the throat of the wormhole, and you aren't cutting through any of the bulk entanglement. In this case, the sort of maximum size is this cut here, where you cut through basically all the bulk entanglement, and you cut through the initial horizon area of the black hole. So the maximum size is the sort of semi-classical entropy of the radiation plus the initial Bekenstein-Hawking.
Just understand the cartoon. So the fact that you have this kind of like increasing size is going back in time in the evaporation of the.
Exactly. So we assumed we're again considering a nice slice where the slice sticks close to the horizon, sort of a constant radial distance inside the horizon as we go deeper into the wormhole. And because the radius of the horizon is getting smaller, that means the radius of the slice is getting bigger as we go deeper. But yeah, this is the like earliest qubit of radiation, right? So it's entangled with something that's deepest in the black hole that corresponds to like furthest black in time. Cool.
Thanks.
Okay, so there's another thing we could do. Okay, and that's to sort of start again with the same cut, but now we sort of just nucleate a double cut, two spheres like right next to each other near the throat of the wormhole. And then we leave one where those spheres where it is and move the other gradually backwards along the wormhole. So eventually it gets to the end and it can disappear. Okay, it turns out that again, this case, the maximum size is sort of just after you create that double cut. And it's now given by, again, the semi-classical entropy of the radiation, but it's now plus twice the sort of final horizon entropy of the black hole. So once the black hole is sort of less than half its initial size, then this one is actually going to be more efficient than the first one. It's worth noting, by the way, you might think this is like a page time. It's actually not. The page time is defined by the semi-classical entropy of the radiation being equal to the Bekenstein-Hawking radiation of the black hole. This happens when the horizon area of the black hole is a bit bigger than area 2. It's like 60% of the area in practice. And that's just because the evaporation is thermodynamically irreversible. The increase in S rad is bigger than the decrease in the Bekenstein-Hawking. So that's just a side comment. So we can then make a precise restricted complexity conjecture for evaporating black holes. Turns out to agree exactly with sort of what you, well, at least it seems to agree, conjecturally agrees with sort of what you get in toy models as well. So yeah, that is, yeah, the restricted complexity is given by complexity of the sort of tensor network, which will, well, I'll call it complexity of the tensor network, complexity of the like unrestricted complexity maybe, which we'll assume is due to like volume or action, and it's like order T, so order the entropy for an evaporating black hole. Then we need to multiply it by e to the half times the difference between the maximum size of the bulge and the larger of the two minima, right? Because that's the amount of post-selection. Okay. And this should be the maximum generalized entropy in the sort of most efficient slicing through the network. So in that sense, it's a sort of mini-max surface, right? It's a minimal maximum cut of all the ways we can slice through the network. And this one is just the generalized entropy of the larger of the two. This is the amount of post-selection. So yeah, so what we find when we do this is that you look at the restricted complexity of the evaporation black hole. This is actually, I'm plotting log of the restricted complexity here. This linear growth here means it's going up exponentially as the black hole evaporates. Keeps going up exponentially because the sort of size of the bulge is getting bigger until we reach the page time. And then at the page time, it's now, yeah, the no longer about the difference between the size of the bulge and the area of the horizon. It's now the difference between the size of the bulge and the semi-classical entropy of the radiation. And so that causes it to then be flat for a while. And it actually stays flat, roughly flat, until we reach this point where the black hole has half evaporated. And now the sort of maximum size of the bulge changes. And that's because the way we're slicing, the optimal way to slice through the network. We now want to use this sort of reverse way of slicing through it rather than the like forwards way, where we nucleate two spheres at the end of the wormhole and then we'll move one back along. And that's, because of this, then we actually find the restricted complexity starts going down exponentially. And eventually, when the black hole has basically completely evaporated, then sort of the restricted complexity stops being exponentially big because it's just become equal to the unrestricted complexity, right? If the black hole is completely evaporated, then we only have one system. There's no entanglement left with the original CFT. It's all gone into the Hawking radiation. And so indeed, the restricted complexity and the unrestricted complexity. So I'm a bit short on time, but I'm just going to make some final comments. So again, sort of, just now we were just sort of assuming some sort of nice slice is analogous to the tensor network, but really we want some covariant definition of what's going on. So for the covariant definition of the thing that corresponds to the minimal cut in the tensor network is the minimal quantum extremal surface, as I said, and it's also given by the sort of maximin prescription, right, where you maximize the size of that minimal cut over all Cauchy slices. The other end of the lunch is obviously the sort of other minimal cut is just the second quantum extremal surface, the sort of larger non-minimal quantum extremal surface. What we want to know is what the covariant definition of the sort of maximum size of the lunch is, right? The maximum bulginess. So for a tensor network, it was the minimal maximum where we minimize the maximum size over all ways of slicing from one way to the end to the other. Right? That's what I was just talking about with the different ways of slicing through the network. But now, that only tells you what it is within one Cauchy slice, right? We still need to know what Cauchy slice to use. The very natural covariant definition to use is just that it's the maxi-mini-max surface. So we maximize that mini-max, that minimum over all ways of slicing, that minimum of the maximum. So first we choose a Cauchy slice, then we choose a way of slicing from one minimal cut to the other. Then we look at the maximum generalized entropy cut within that way of slicing. Then we minimize that over all ways of slicing. And finally, we maximize that mini-max over all choices of Cauchy slice that contain the two ends. So this is completely conjectural, but it's the very natural covariant definition you have. And you can argue, given everything being sufficiently well behaved, that this will be a sort of third quantum extremal surface. So there's a sort of natural definition, of a Python's lunch covariantly in terms of three quantum extremal surfaces, sort of small, large, medium in size that correspond to the tensor network having a smallest cut and then the largest thing and then a medium thing. And in evaporating black holes, at least in very simple cases, we can actually explicitly find the quantum extremal surfaces that correspond to the sort of maximum bulge size in these two ways of sweeping through the network. So the ways of sweeping through the slice where you sort of start with a sphere appearing at the end of the wormhole and then push it along the wormhole forwards actually corresponds to a single sphere that sort of sits inside the shell of collapsing matter that forms a black hole. And it sits sort of just inside the event horizon at the point where the apparent horizon has got within like a Planckian distance of the event horizon. It's just a thing you can calculate. It was actually calculated in both my paper and in AMM way back in June, though we obviously didn't care about it so much. Actually, sorry. No, this one was not calculated in my paper, though it easily could have been, but it was explicitly calculated in AMM. Apologies to them for claiming equal credit for having explicitly calculated it. And that turns out there's also a surface that corresponds to this reverse way of sweeping, where we nucleate two spheres at the sort of end of the wormhole and then push one backwards along it, and the other one just goes and sits at the normal, non-trivial quantum extremal surface. So in this case, the quantum extremal surface is a union of sort of two spheres, and they both sit just inside the sort of normal quantum extremal surface that determines the page curve. So there are these two black dots in this diagram. And in general, this is hard to compute. It involves the bulk entanglement entropy of like two regions. But you can actually calculate it in sort of JT gravity plus free fermions. And yeah, the sort of takeaway of all of this is that you can do covariant calculations and they exactly reproduce all the sort of qualitative conclusions that I made about the restricted complexity curve with precise covariant calculations, albeit ones that don't have a precise connection to what we want to calculate. We just have this analogy argument for why they should be relevant. Okay, so let me just make some final comments. Why should you care about this? Well, one nice thing about it is it's saying that sort of non-minimal quantum extremal surfaces matter too, right? Even if the minimal one is the sort of really important one that determines the entropy, then the existence of these non-minimal ones has important consequences for things like complexity. It also tells us that there's still like lots of stuff to learn from the semi-classical geometry of an evaporating black hole, right? Like, this thing that a few years ago everyone thought was just completely a wrong description and needed to be totally overhauled and replaced. It's not only giving the right answer to the page curve and stuff, it's continuing to like give answers that fit with our toy models and that teaching us new and interesting things. This is maybe more of a side part comment, but it's also the case that if you look at an evaporating black hole and then you measure the Hawking radiation in some simple way, then you can actually make a state with a large unrestricted complexity, but a very small volume or action. You sort of get a one-sided Python's lunch where it like a Python's lunch where the minimal cut is 0, but you still have this non-minimal cut with a bulge behind it. So what does this mean? Well, one possibility, as Alex said, is that this state somehow has large quantum corrections to the volume equals action definition, but the quantum state is very simple, so I would prefer not to say that. I'd prefer to say that what it suggests is that volume and action is actually dual, if anything, to the sort of size of the minimal tensor network needed to prepare for the state, not to sort of the unitary circuit complexity of the state. So when we define holographic complexity, we should actually allow post-selection generally. We want it to be dual to volume or action. Another minor comment is that actually Harlow and Hayden's estimate of the complexity is wrong. We have a square root improvement over it. And you can actually see this in toy models as well. Our Grover search algorithm just works in toy models and improves the complexity by a square root factor. So that's mildly cool. But yeah, just to finally end, we were encouraged to end with some provocative theses. So I just have one, which is I argued in this talk that sort of if you have a Python's lunch, that leads to an exponential complexity in the holographic dictionary, right? You have these operators in the Python's lunch that are seemingly simple in the bulk, but at least their boundary reconstructions restricted to one region are exponentially complex. So you can naturally ask, what about the converse of this statement? Could it possibly be true that whenever we have an example of the holographic dictionary being exponentially complex, then secretly it's because there's some Python's lunch sitting there. Let me give a couple of vague arguments to that. This is something that some collaborators and I have been thinking about on an ongoing basis, though we're not really close to being done. So in particular, sort of causal wedge reconstruction is easy compared to generic entanglement wedge reconstruction. We think it's a low complexity thing to do. There's some reason to think that actually by doing causal wedge reconstruction, but sort of changing the boundary conditions and using time folds and stuff, can actually push the causal wedge out all the way to the nearest quantum extremal surface. So what would that mean? It would mean that if anything that's not behind a quantum extremal surface, you can do by sort of things that are morally equivalent to like HKLL or causal wedge reconstruction. Anytime something's not hidden in a Python's lunch, then it's like easy to reproduce. There's some seeming counterexamples, or things you might think are counterexamples to this, where you have a highly complex dictionary but no lunch, and they mainly show up in sort of non-evaporating black holes. For example, just reconstructing a late time interior mode in a non-evaporating black hole, we think it's exponentially complex. The volume of the wormhole, as Adam will be talking about, in a non-evaporating black hole is exponentially complex, we think. But it turns out that sort of whenever you consider a sort of non-trivial code space of such states, so it actually makes sense to really talk about reconstructing an operator. And then you look at mixed states in that code space, which again, you need to do entanglement wedge reconstruction, then suddenly a Python's lunch shows up. So actually, secretly, there was a Python's lunch all along. So yeah, on that note, I'm done. Thanks everyone for listening.
Thanks a lot. Let's all unmute ourselves and thank Geoff for the nice talk. So we have time for 1 or 2 questions. So any questions for Geoff?
So I'm not sure this might relate to the causal wedge point that you made towards the end, but if I describe, like, say, empty ADS with a funny set of coordinates, I can make it into a topological black hole, right? I mean, I can have a set of coordinates which make me think that the empty ADS is a black hole. Would I have a Python lunch in a geometry like that?
I don't think so. So the definition of a Python's lunch or not is like covariantly defined, right? We can define it in terms of this sort of maxi, mini maximization and stuff, or just in terms of having 3 quantum extremal surfaces. And quantum extremal surfaces are covariant things, and MTADS only has 1 for any given boundary region. So I think, yeah, maybe we'd have to think about it harder, but I think you wouldn't. One thing that's true is if you look at just sort of 2 regions in ADS, maybe, how do let's see, let me go to a whiteboard. Okay, if I look at sort of 2 boundary regions here and here, then now I sort of have 2 quantum extremal surfaces. And if I sort of want to sweep from one to the other, I have to do a topology change at some point, but it's still the case that it gets bigger and gets smaller again, right? And there's really a natural streamal surface that characterizes the size of the bulge, which is just a sort of crossing X. So already here we have a Python's lunch. Now, I'm not sure if I would necessarily want to conclude from that sort of entanglement wedge reconstruction of some operator here on the left and the right is exponentially complex. And the reason for that is that in a black hole, you sort of have confidence that the dynamics are like scrambling and stuff. And in this case, it's not necessarily true, but it's at least the case that it could be a lot more complex than, yeah, it is still in some sense hidden behind a Python's lunch. So you can have Python's lunches in empty ADS, but just not for a single boundary region. Is that helpful?
Yes.
I have a question, sorry. So Geoff, you mentioned that you can reconstruct all the way, or you can reconstruct all the way up to the quantum extremal surface.
I'm speculative.
I think you get stuck on the nearest marginally trapped surface.
I think you should be able to get past a marginally trapped surface by going backwards in time as well.
I think that's only if you prepared your state in a certain way.
We should maybe discuss this. I don't want to make any firm statements, and I think you're, yeah. But you don't think, What do you mean by prepared your state in a certain way?
Well, I think if you imagine you start with the thermofield double and then you throw in a bunch of shocks, then certainly it's clear that you can undo those shocks and you can bring your quantum extremal surface back to the situation where it's at the event horizon. But if you, I mean, the way this construction essentially works, the important thing is that you have vanishing expansion in the outgoing future direction. That's also true of the nearest marginally trapped surface. So it's not clear to me what the difference is if you're doing a construction where you're essentially removing the stuff that's falling across the horizon, what the difference is between the nearest quantum extremal surface and the nearest quantum marginally trapped surface.
I think that's true, that if you remove the stuff, like it's certainly true you can't get beyond a marginally trapped surface, but I think you can stop a marginally trapped surface being marginally trapped by going backwards in time and removing stuff.
Potentially, if the marginally trapped surface is outside of any past horizons, but if it's not, then it's not clear to me that you can do that.
I agree, it's not clear. Let me give an example where you can't do that. Let's say you don't know when the shocks were thrown in, right? That would be an example. But now I claim if you, and I have not calculated this rigorously, but I think it should be true. If you don't know when those shocks were thrown in, and you look at sort of a mixture of the different states with shocks thrown in at different times, then I think you'll find a new quantum extremal surface that sort of, so you won't be able to get inside, you won't be able to get back to the original thermofield double state, but that's because there's a new quantum extremal surface much further out.
Right. My point is, if you have a long wormhole and you didn't prepare it by throwing in shocks from the thermofield double, then you could have a marginally trapped surface. I mean, you can do that, right? I mean, Aaron and I had this construction where you had you did the coarse grain spacetime from a marginally trapped surface. It's a longer wormhole, but you don't construct it by throwing in shocks. And
yeah, but in that case, there's a quantum extremal surface that's like separated from the marginally trapped surface.
Yeah, I'm just saying that's an example of a situation where you can have a long wormhole that's not prepared by throwing in shocks from the thermofield double. And in that case, you can have a quantum marginally trapped surface that's outside of your, that's behind the past event horizon. So I don't think you can get past that. I don't think you can do that and still preserve the GSL.
What stops you changing the boundary conditions so that it's no longer behind the past horizon? This could be true, but my sense is that if it is true, then there should be some fundamental obstruction that.
Well, it's possible that you have different types of marginally trapped surfaces, and some of them are nice ones that play along, and some of them are ones that don't.
I agree. I don't want to make any claims about what the actual. It was a provocative thesis.
You managed to provoke some of us.
Yeah, exactly.
Sorry to cut you guys. I think we're running behind on time, and as a citizen, this is starting to bother me. That's my cis nature. So I suggest we keep this discussion for after the second talk, where we'll have more time for questions and keep on discussing the ones that we haven't all agreed on. So first, let's all thank Geoff again for the nice talk. So again, we can unmute ourselves, and let's take a